Hello, I am Luis Zapata. I am from Mexico. I am from the Institute of Astronomy and Astrophysics, part of UMA. I'm going to talk about planets forming disks in the ALMA era. This is one session part of the school. I hope you enjoy it. Here is the outline. The outline, you can see many topics that I'm going to talk in this presentation. You can see that I'm going to talk about the phases of the star and planet formation, the physics of the protoplanetary disk before ALMA, the ALMA observatory, this stability, evidence of planets information. And finally, I'm going to talk about the complex molecules in disks. Let's talk about a little bit about the formation of the stars. You can see here a really beautiful image from the Hubble Space Telescope. You can see the scale is more or less 1 parsec. The head of the horse in this beautiful nebula. Here is where the star and planets are forming inside of these really nice clouds. The idea of forming this kind of objects is that you have a really large scale. I mean, you can see the parts of the scale going through the solar system scale and planet scale. I mean, there are really large numbers that you can see trying to go from a really large scale to the really small scales. There are 4 phases where the stars actually are forming. We actually classify for class 0 to class 3, the different phases of the star formation. I'm going to talk to you about this kind of different phases. The first phase you can see here in this image is also really beautiful image from the ALMA telescope. You can see a binary system. There are actually 2 stars. There are contours that you can see in gray scales. Those scales are tracing, or those contours are tracing the protostars that are really, really young and have this kind of molecular outflow in different directions. You can see here the colors represent the different velocities. The red ones are the red-shifted velocities, and the blue ones are the blue-shifted velocity. I mean, there is gas that is actually approaching to us, and the red ones are receding to us. And the green, I mean, you can see some gas that are, the color is green, is more or less the cloud. In the really early phases of the star formation, you can see that it's really important the envelope of the cloud. Here in the green scale, you can see that it's almost covered to stars, and this is really important. The main thing about this class 0 star is the first step of the formation, and there are a few things that we already know about this step. You can see there is a really high accretion phase, that is a inflow, presence of bipolar outflow that I already showed you in this image, bright sources and the Submillimeter regimen. I mean, you can see that if you see the seed, here is again another small picture. You can see here is the class 0, and you can see the emission of the black body that is really cold, tracing a really cold material, mainly dust, also dust, and peaking in the millimeter and submillimeter region. This is really important because this is the first step of the formation of the star. The duration of this phase is really short. I mean, you can see here the numbers is more or less 10 to the 4 to 10 to the 5 years. I mean, it's really large number. The temperature is also really cold, 10 to 100 Kelvin. I mean, it's really, really cold there in this kind of phases. And this is the name of this phase is the protostellar phase that is really important to start forming this kind of objects. Here, something that is really important is that the mass of the envelope is really large compared to the mass of the star. I mean, the mass of the star is really small, and you have a really large envelope, and also you start to have some kind of protoplanetary disk. Here is really also a picture of the cloud, the envelope. There's some kind of disk, and this kind of outflows in this direction. I mean, you can see the scales are really large, like a 10,000 AU. That is a point 1 parsec. I mean, it's also more less than a parsec scale. The second phase, the name is class 1. I mean, the stars already start to involve in more different phase. You can see also a nice picture here from the Hubble Space Telescope, where there is some kind of holes now when the prototype started to clean all this envelope and is started to see bright in the infrared emission. Also, the accretion is really important. The presence also from bipolar outflows, I mean the mass ejection. There is a really bright source now in the infrared. The duration is also really short. It's only 10 to the 5 years. The temperature is a little bit increased. It's something like 50 to 500 Kelvin. And you can see, I mean, the envelope of the mass is still really large compared to the mass of the star. There is some kind of Keplerian disk. I mean, here in the picture, you can see now the scale is really small scale compared to the last one. You can see the outflow that is in this kind of two direction. In the orange, you can see the disk that now there is some kind of Keplerian motions, and the info envelope is still there, but it's not so bright. The class 1, I mean, is characterized by infrared excess, the black body radiation from this kind of dust that is still there and really important. And this phase is still, I mean, the protostar is still really accreting mass. The next step is the T-Tauri phase. I mean, you have here actually one of the important T-Tauri stars. You can see this is now really bright in the optical. I mean, there is some kind of clean gas from this position. There is some clouds, but now there is no important. I mean, the star started to really clean all the molecular cloud that is surrounded this star. This phase is also start to be important in the optical wavelets. You can see that now we have a bright source in the optical wavelets. We have a really faint optical bipolar outflow. I mean, the mass ejection start not to be really important. The scales now you can see is actually smaller than the last step that I already showed you. It's around 100 AU, and this is more or less the size of our solar system. The duration is around 10 to the 6 years. The temperature is now increasing. It's almost 5,000 Kelvin. This is known as T-Tauri phase that I already mentioned this. The accretion is now not really important. I mean, the accretion is start to be less important, and you can see that now the star is considered that we are starting to really be on the pre-main sequence star, and the envelope that really surround this star or this really young star is almost disappeared. I mean, you can see in this picture that the envelope is almost gone. And the nice thing also that in this phase you have the emission actually from the star, from the optical, and you start to have some emission from the disk that you can see now. The emission from the dust is not really important, and now the emission from the star start to be really important in these phases. The next step that we actually have here is the class 3, that is more involved with the star. You can see from here, actually, the scales is more or less scales of our solar system is like 100 AU. More or less, I mean, after this phase, almost all the planets and the stars are formed, and we have a solar system as we really know now, without really much dust and not really much gas. Everything seems to be that is erased and is photoevaporated from the radiation from the star, and maybe also fall to the star some material in this phase. What are the important things about this class? Pues is that you have also the bright source of the optical. I mean, you have already formed the star. The duration is almost really large, like 1 to 50 to 10 to the 6 years. The temperature is something around 6,000 Kelvin, is more or less the temperature of the sun, the atmosphere of the sun. There is some kind of thin debris disk, and the most important thing is that people really actually think that in this phase we started to have the planet formation. This is that the people already thought. Many actually reviews mention that maybe in this phase is when the planet formation start, and you have mostly all the different phases of this planet formation in this step. In this image, actually, you can have, or you can have a different things. Here, the seeds of the different stars. That is some kind of survey. In this survey, you can see that mainly from this survey there are class 3 objects, and you can see that the spectra is dominated by a single seed, mainly associated with a black body from the start, and probably some contribution of the disk also in these four stars. The temperature you can see is also around 3000 Kelvin. That is really hot compared to the other phases. And the idea is that in this phase is also classified one like a pre-main sequence star. And here we have actually the the beginning of the planet formation. But in the next, the slide, I'm going to show you that maybe this is not really correct. Look that the planet formation seems to start before of this phase, as we already have some evidence. And let's talk a little bit about the physics of the planetary disks. These are really important for the accretion to the start. This is the channel that the mass also from the envelope is going to be, I mean, flattened, or is going to be to the start. And from here, I wanted to show you something that is really important to have a disk. There are two phases that we have in the disk. One is the rotation, and the other thing is the infold. If you combine these two things, something that is rotating and something that is infalling, at some point, it's going to be rotating and it's going to be infalling. And in some point, something is going to happen with this actually cloud that is going to be elongated, because the infall is going to push on this direction, and the rotation is going also to start to flatten some kind of gas or molecular gas. And you're going to have this kind of disk at some point, something that is really, really thin and is rotating to the really large velocity. You also can have this kind of conservation on the angular momentum, that if you have a really small part of the disk, is going to rotate more quickly than the outer part of the disk. And then also you're going to have that really close to the star. I mean, all the material is going to be really fast and trying to go directly to the stars. And this is going to allow to the star is going to be actually grow up in size and also in mass. And that is the reason that the disks are really important, because I mean that is going to allow to the star to grow up in mass and in size. Here is one really nice actually picture from one object that the name is the HH211, that is an outflow. You can see here in this image. Here in this image I can show you in grayscale the H2 emission, I mean the molecular emission from the H2. And in the red one, you can see actually one molecule that is emitting from this really dense part of the cloud, that the name is N2H plus. And the idea from this that I wanted to show you is that in the really, I mean, large scales, you can imagine that here in the really center where is the X letter is the disk. And here the disk is really small compared to really this kind of structure that is traced by the red contours. And in the red contours, you can see some kind of envelope. And the envelope, if we go and see the velocity field, you're going to have a really nice, I mean, rotation. You can see that is the gas is receding to us and the gas that is approaching to us. And this is the main idea, that if you have a really large structure that is rotating, maybe with a really small velocity, if you go to the really small scales and the momentum is conserved, you're going to have a really, really high velocities rotating around the stars. I mean, even when you have a really small velocity and a really scale, if you go to the really small scale to the disks, the velocity is going to increment, and this is because of the momentum conservation. And in the really, I mean, middle part of this kind of structure, you're going to have this kind of flattened structure that the name is called the disk. Accreting disk is the name of this kind of structures. And more or less the scales you can see is like 100 AU. I mean the scales of the protoplanetary disks. And this is why we have some kind of this kind of size of that our solar system actually is like that. Another point about the disk is at some point the disk is actually they are going to really start to be some kind of evolution from the disk. You have here four phases that you can have in the disk. One is actually the first. You can have the start. You see in the blue colors and the brown dots that represent the dust and the gas. You can see how actually the UV photons from the star is actually hitting the disks. And from this part that is really beyond the disk, I mean, the radiation is not really important. You still have accretion to the star, and the star is growing up in size. But if you really go and see after some point, you're going to see that the most of the dust is start to sitting down in the middle plane. And in the middle plane, actually, the dust is going to start to grow up in size. And these kind of things, you're going to really have that not really small dust compared to the interstellar medium. If not, you're going to see those that have sizes of the millimeter size or 1 centimeter or even larger centimeter, because the dust at some point is going to start to settle down in the midplane, and this is going to really have a larger size of the dust. And then at some point, I mean, the photoevaporation is going to be important, and you can have a really large particles, and then all this kind of disks is going to start to disappear. I mean, mostly the gas is going to be photoevaporated. You can see here the evaporation flow. And at some point, most of the particles really close to the star are actually going to be without gas. Only the gas is going to be present in the outer part of the disks. And the really, really, I mean, if you go and see this kind of evolution later on, you're going to see that most of the gas is gone, and you're only going to have this kind of, I mean, particles, really large particles that form some kind of debris disks or some kind of disk that is with no gas. I mean, the time to really reach all these phases is going to take something like around 10 to 50 mega years. And I mean, it's really small compared to the life of the stars. But the idea is that at some point that you have, I mean, this kind of really large grains, you're going to start to have the planet formation in this disk. And the disk have to really evolve in different phases, have to, I mean, the dust have to really sit it down on the midplane to really grow up, to start to have some really large particles, and these particles are going to really evolve to form really small embryos, that these small embryos are probably form planets at some point. Here's a really nice example of, of this kind of sitting. Those actually, this is a picture from ALMA from RU Lupi. RU Lupi is one actually star that is also just forming. Here in the blue color, you can see the CO emission, I mean the monoxide, the carbon monoxide emission. You can see some spirals, really well defined, and it's in really large scales. But in the really middle part of this actually molecular disk, we have the dusty disk. I mean the emission that is traveling mainly from dust. The particles here, I mean the size of the particles are really large, probably 1 millimeter or larger, that is emitting this kind of radiation. This is more or less 1.3 millimeter emission. And the nice thing, as you can see, that I mean, the emission from the continuum from the dust is localized in the really middle parts of the disk. I mean, really inner part of the disk. And most of the gas is really on the extended part of the disk. And this is quite nice, because the idea is that all the dust is already settled down in the midplane and go through the really small parts or really inner parts of the disks. And this is one of the evidence that we have really sitting down, and this sitting down dust in the midplane is really have a really large particle like 1 millimeter or even larger. And this is one of the evidence that we have here. This is another nice picture from actually the Hubble Space Telescope. This is the optical and infrared emission. And you can see different panels, and also you can see the scale that is 500 AU. And here you have a different actually disk. You can see a really dark lanes, and also bright lanes. The dark lanes is actually the disk that is absorbing the light, the optical light, that is arising from the protostar in the middle. I mean, the phases is already class 1 and class 2. I mean, they are already bright in the optical. But you can see the really bright lanes that's supposed to be the really this that is surrounding the young stars. But the problem with this, I mean, images that we cannot really go and see in the disk and try to see some kind of planet formation. We need I mean, another tools to really go and see how the planet formation is actually, I mean, working here, and we need to move to other observations. And one of the best ideas to really go and see the planet formation is going directly to the submillimeter and millimeter emission, where most of the dust is actually emitting here. And one of the really nice telescopes that we can use is the Submillimeter Array that is located in Mauna Kea, Hawaii. And you can see here one of the nice pictures of the actually 6 antennas from this telescope. And here you have some kind of survey made by Andrews in around a few years ago. And from here you can have you can see the different disks emission from the dust. Here is in different colors, I mean, going from something that is faint, going to something that is bright. And mostly are really rounded, all the emission from the disk. You can see from different objects. Here is the name of the different protostars. And the idea is that you have a different, actually, morphologies. Some of them are show some kind of hole in the middle. Others actually don't really show this kind of hole. There is some really bright emission in the middle of the position of the star. And from this image, you can see that we can go and see the disk really clearly and try to see how I mean, planet formation is taking place in this kind of disks. I mean, the emission from this kind of disk is mainly, at these wavelets, is mainly large grains, and I already showed you in another, I mean, slides. And this is a really nice picture because can show you the different parts that is emitting in different wavelets. For example, you can see that ALMA, I mean the ALMA observation, also the submillimeter array observations, I mean, is showing you the really outer part of the disk. You can see in this kind of red colors, and this is really part and cold part of the disk. You can also have this kind of emission from the Hubble telescope, another telescope that also are located here. Mainly, I mean, the emission is arising from the midplane of the disk. Is the part that we are seeing the ALMA and the submillimeter emission. You can see also some kind of the mid-infrared is also observed more or less in the middle part of the disk. I mean, not so cold and also not so hot. If we go to a really close part of the disk, we can see actually emission from the near infrared. The continuum emission is approaching to the star. And if we go really close to the star, we're going to have also some UV emission, probably also part of the optical emission. And we see emission from different molecules and also from atomic and also on the polar emission from this, this kind of molecules. And more or less, this really shows you that we are having a different parts of the disk is emitting in different wavelengths. But the main idea that all the observation that we have from ALMA that we are going to start to analyze is coming from the outer part of the disk, not really close to the disk. Maybe this is one of the reasons that we also have this kind of holes in the submillimeter regimen. And what is important of this ALMA observation? ALMA, as you know, is a new telescope, not so new, but it's still new. I mean, the ALMA has some kind of 66 antennas from different sizes and in different forms. And the idea is that you can connect all the antennas and form a really, really large telescope. This is the interferometry, idea. And here some facts about the ALMA observation. You know, the interferometer works on the millimeter and submillimeter wavelengths. This is located at really high sea level. The altitude is something like 5,000 meters. The resolution is really, really nice. You can see that it's actually better than the Hubble telescope. It's around 10 milliseconds. As already mentioned, that ALMA has like 66 antennas, something from different sizes, have a 10 receiver bands going from 7 millimeters to 0.1 millimeters. This covering a really broad range of wavelengths. And you can see a really different things in the different wavelengths. And the largest, maximum baseline is around 60 kilometers, 16 kilometers. The separation between antennas. That really give you a really great sensitivity and also give you a really nice, I mean, angular resolution. And the combination of those two things that make you a really nice images and really with a really great fidelity. And this is a nice idea that we can go and try to study the disks in a really great detail. And here is more or less the how ALMA actually works. You can see the signal from the many stars, from the 60 signal stars. You can see the incoming signals that you have this kind of parabolic, dishes. All the light is reflected and is sent to the front end. In the front end, you can have and actually send it to the correlator, and you have some kind of signal that is not digital and it is transformed in the backend, and after this is sent to the really brain of the telescope, that is the correlator. And in the correlator, all the interference with a different telescope is made, and after this you can have the data that is already combined and you can start to create images. And it's really nice because you have, as already mentioned, really 2 points and really important points. The high sensitivity and the angular resolution. And let's start to talk a little bit about the planet formation. You can, here is a really nice image from from one person that already is showing the protostar. Is surrounded by this kind of disk, but in the really small part of the disk, you can see there is some kind of planet forming. You see some kind of spirals that maybe is associated with this in falling material, now falling to the planet, and the planet is actually forming and curving this kind of gas, and you see some kind of gaps here. This is a really an artistic impression. I mean, we already know about some of these things, but this is how we really imagine that the process is happening. And this is one of the surveys that already, I mean, the ALMA people do. The name of this survey is the sharp, and you can see why is the sharp. This substructure a high angular resolution project, the sharp. And the idea was to try to imagine one of the closest disks. I mean, you have like 20 disks that are really close by to us, and try to reveal all the morphologies that those disks actually are presenting. And here you have a really like a zoo from different position of the disks. Some disks are close to the plane of the sky, some are not. I mean, it's probably in a different angle. But here you can see that the main thing is you have some kind of rings, some kind of gaps, some kind of spirals, and you see really, I mean, there's this really rich structure from different parts of this kind of survey. And the idea is trying to explain why we have this kind of gaps or why we have this kind of spirals. If we go and see different actually observation, we are going to have a better idea that how the planets are actually forming. And one indirect evidence that we have that is actually forming planet are the asymmetries. The asymmetries, as you can see, this is another survey that, that actually the people in ALMA do. You can also have a different disks. It's again the continuum emission. I mean, it's the emission from the small particles in the disk. And here you can see really clear the holes. There's really there are many holes. Also, you can see that really large asymmetric. I mean, you only see really bright part of the disk is emitting in these wavelets. You also have gaps. You can see here the kind of gaps. This is really clear also in this disk. And the idea is that maybe most of these actually morphologies are related with planets that already are forming. I mean, some people is thinking that maybe these kind of gaps are associated with planets that are already forming in this kind of disk. That also there are some also options, and the people also think that maybe it's not only planets, but maybe there are also some other processes that are actually occurring on the disk that can produce this kind of gaps. But now I mean the main idea that from the people is actually that maybe are associated with disks. And how we can explain that we have this kind of structures that are not really tracing the entire disk. I mean, you can see from this disk that is really close to the plane of the sky, that is the idea that you really see the really round thing. But in this case, you only see a really part of the disk that is emitting. And the idea is really easy, and it's actually also explained about the planet formation. And here is one of the pictures that the people is really trying to explain these kind of things. You can see that in the disks, you have a really small particles that I already told you that the particles are something around 1 millimeter, something like 1 centimeter. Here is located the stars. Also, you have some particles around the stars. Here, the red dots tracing the position of the planets that are forming. And here in this part, actually, you see a really large particles that is also emitting in these wavelets. And the idea that you have some kind of different pressures in the disk because you have already planets that are forming, and those planets actually change the pressure of the gas that is on the disk. And the main idea is that this change on pressures or also in density, you can have some kind of those tramps that you really have some kind of really large particles. And the idea that you have this kind of thing is that you have some kind of those tramp here. You maybe have some planet that is forming in the middle. That is the main reason that maybe this you have this kind of holes. And the the planet formation is actually causing that you have these really large asymmetries that the dust is actually emitting. And this is really nice because it's one of the indirect evidences that we have that probably already, the planet formation is taking place in this kind of disks. There is another nice thing. I mean, if we have planets and are actually circling the disks, look like at some point the disk, with planets forming, are going to be stabilized and are going to be really smooth. Here I actually show you one of this kind of simulation, SPH simulation of one of the self-gravitating disks showing that in one part is snow with planets and in another part of the disk is with planets. And if we go and see the differences of this kind of disk, one with one planet and the other one without planets, you're going to see that the disk that is not associated with planet, you can see there is many spirals cycling around the the disk. But the another one looks like more smooth. The density and the features of this disk look like more like a really smooth, and you can see some kind of holes and the things that we already see in the different planets. You can see here, the comparison. This is with a many spirals, and this is with a really smooth tracers. And this is one from the other actually evidence that we have that maybe the planet formation is already taking place in this. So this is really important because if we go and compare directly with the observation, this is actually different picture from the observation. This is the the simulation that I already showed you. But now here the idea is that I am showing you the simulation of the observation. You can see the this without planets. You see some spirals, and the disks with planets. You see that it's really round, and we go and compare. With the simulation that is azimuthal average. This is more the the theoretical disk. You can see that we actually do some kind of subtraction. You can see all the spirals here that is well defined, and the other case you don't see the spirals. And this is the idea. And if you have the disks actually associated with this that we already see, that we actually have this kind of gaps or this kind of things or future that we already see. For example, this is one observation from the HL tau, that is another kind of disk. This is an image that is the projected, and we compare with the simulation with the protoplanet that is already forming. You can see this really, I mean, like the observation, you see this kind of the gaps. You can see also have you also see have some kind of one spiral also, and the idea is that when you really have this kind of planet formation, the disks are really similar, the things that we really have. The other indirect evidence of the planets are, as already told you, the gaps and rings. And here is another simulation from the Piero in 2015. And here the Piero actually put three planets. You can see here the three planets with the different masses, Jupiter masses, and are localized in the different places. And the different places are mainly on the gaps of this image. And we'll go and do the simulation and also do some kind of, try to simulate the observation. You are going to see that they are really similar when you put a planets and the things that you get. I mean, it looks quite similar, and that is the idea that the people now really think that here in the middle of these gaps, you probably have already planets that are forming inside of these gaps. But the thing that we actually don't see this kind of planets maybe is because are really faint in the millimeter emission. I mean, they are probably more brighter in the infrared emission, as I'm going to show you later on. Another evidence that we have for forming planets are the velocity kinks. I mean, if you go and see the velocity, fields of the disks, you're going to have some kind of disks. And in this kind of emission from the CO or other molecules, you can actually start to see one of different things that you probably expect when you have this, when you have planets forming, or when you really don't have planets forming. And here, the thing that I show you is one observation of these disks. I mean, the CO emission from the disks. This is also, image from the ALMA telescope. And from here, you see the name of 16329. And from this disk, actually, the main idea is when you see the velocity fields, you're going to see some kind of kinks or some kind of deviation of the gas, and this is maybe really associated with the presence of one a really small disk. For example, this is a continuum also from the grains from the disk. You can see this really nice gap. And in the middle of this gap, these people from this study is saying that here they actually report some kind of kink. You can see some kind of deviation, and this deviation is probably due to the presence of the one planet that is forming. If you go to and you go and see the other side of the disk, you're going to see that there is no kink. Looks really, I mean, really straight, the gas emission from this channel velocity, and you're not going to have this kind of kinks. But if you go to other side of the disk, you see where the position of the planets is there, you're going to see this kind of kink. that is some kind of perturbed, the gas is perturbed by the presence of the protoplanet that is forming here. Here there is some really nice picture when you see the two different part of the disk. There is some kind of disk emission from this part, also from this part. You see also the continuum emission. The position of the planet is more or less here, where is located the gut, and you can see the velocity kink, the perturbation that is due to this protoplanet. There is also some more, works from this group, and you can see that in many disks, they seems to really find this kind of kinks, and they propose that in many of these disks, the planets are actually forming because they study the gas and actually go and see the position of the of the planet. Another nice thing is when you have some kind of protoplanet, that is forming on the disk, you can see that is forming this kind of spirals that already show you in another images. But if you go and see directly the gas seems to actually falling to to the to the planet. The protoplanet is located here. You have the blue shifted emission and red shifted emission that seems to form some kind of really circumplanetary disks, and those flows are actually falling to the planet, and those things that's supposed also to see it in the observation, but maybe are so faint that it's not really clear to see kind of this flowing emission to the protoplanet. Another thing that we actually have is that we already have direct evidence that the planet are forming in this kind of disks. And one of these evidence came from this disk. You can see, the emission from the dust emission that look like a donut. There is some emission actually in the inner part of the donut. This is a millimeter emission. This is emission actually traced by the ALMA telescope. You see the disk and you see the hole, but in the middle of the hole, you see some really small structures that look like are associated with the protoplanets. Here, the protoplanets were actually detected in the infrared emission, and they are really faint. And here are more or less the characteristics. You can see the different telescope that already actually show the protoplanets. One are the ALMA telescope, the BLT, and you can see the emission from these protoplanets that are really forming in these disks. What are the masses of this kind of protoplanetary? Pues really, there are a really small one. This is like one Jupiter mass. This is like 4 Jupiter masses. Here some actual number for the period and the distance that they have from the stars. And this is really nice because you are now in this really seeing the formation of the planets there in the middle of the disks. Why we don't see, emission in the other disks is maybe because are really faint. As already told you in the millimeter emission, they are probably brighter in the infrared emission. And the idea is that maybe we go with really deep observation, we can actually go and see this kind of disks and also this kind of protoplanets forming just there. There are also some molecules that are complex molecules. The complex molecules you can see here, the metallocyanides, that is really complex. This emission is associated with the name is MWC4A0. And from here, you can see that, I mean, you have the different emission from the different species. And this is a really complex. I mean, we already know from the other observation from the whole molecular cost that we have actually more complex molecules. But look like it's really difficult try to find molecules in disks. That means these are more involved. I mean, like class 3 or class 2 is more difficult to find, maybe because they are already, I mean, on the ices or in the dust, and it's not really easy to try to detect it. Maybe the emission is already faint, that you already see in this image. There is also some detections from this kind of molecules from other disks. But it's really important because, I mean, if you find molecules that are more complex and more complex, you can really trace how these really complex molecules can go to the comets or can go to the planets, can go and deposit to the atmosphere of the planets. And the idea is that the people is now really interested in trying to go and see more complexity in this kind of disks. And mm, mm, there are many actually groups that they are trying to really find this kind of more molecules like glycine or other kind of molecules. And the idea is that when you already have these molecules, you can also start to think about the life on these systems and how it's going to proceed with these complex molecules that already the people actually detected. And you can see there are actually different things. I mean, you have now the how the stars are forming, how this star actually forms some kind of really thin disks that is surrounded the protostar. After some point, this actually disk is start to be more involved and start to form really large grains with sizes that go like 1 millimeter, 1 centimeter, and this kind of disk, and it actually start to form some protoplanets that they are going to grow up in size and form this solar system. After some point, I mean, we already understand all these steps. When we want to really go and understand more the planet formation, why we have a different sizes of the planet and a different position. If you go and see another system, I mean, there is a really large variety of different planets. And this is the idea. I mean, we can really have and see how these planets are forming in different disks that are really large and really small and with a different sizes. That is also important. And for me, for this part is all, I think, and I hope you really enjoy to see all these really nice actually pictures and really nice images that we already have around it, and we started to understand more the planet formation. Thank you and ciao.